Hey AP Calculus students! This video is going to walk you through the 3 problems that I asked you to take a look at for homework. 2 were from the notes, and then 1 was also in the notes, but it was from an AP practice exam. So I want to go through these examples with you in case you're having trouble getting started on any of them, and also so you have a little bit more context behind what it is that we're looking at with each of these scenarios. So the first problem that we're looking at, problem A, is talking about projectile motion. So if you're taking physics right now, that's probably something that you've talked about a lot. And if it's something that you haven't taken physics before, you probably talked about it in algebra too. So whenever you're launching things up in the air, they're going to follow a quadratic path of motion. So something like this is how you can picture if you throw a football or if you launch a rocket up in the air, that's the path that it's going to follow. So when you're looking at a projectile, you're usually interested in 2 different things. One is how high it goes. So we're interested in the height value, like this. And then the other is the range. So you can really just think of it as your horizontal distance, which is what we call the range, and your vertical distance, which is going to be the height. So when it comes to launching these kinds of projectiles or tossing balls or launching rockets, the way that you can talk about this distance, the range, is what we're given in this formula here. So let's break down the different parts of this formula. So like I just mentioned, your R value is your range. That's how far whatever you're launching is going to go. Then in this formula, you have V squared, which is the velocity. So that's how fast you originally launch it. So you can imagine a football quarterback is probably going to throw a football a lot harder than maybe a 5-year-old who's playing around at home. So that shows your initial launch velocity. And then G is your acceleration due to gravity. Now, I want you guys to have a solid understanding of the different values that are going on in this equation, so that way it makes physical sense what you're solving for. But kind of the good news here is V, the velocity, and G, the acceleration due to gravity, are constants. So it really doesn't matter what they are. They're just going to come along as constant values, like a 2 or a 5 would, as we take the derivative. Now, the way we know that they're constants and not other variables is based off of the question that's posed to us. The question asks us which angle of elevation gives the maximum range of the projectile. So what that means is range depends on angle, and that's the only thing it depends on if we're going to be able to solve this problem. So velocity doesn't matter, and then how quickly things accelerate back to Earth are just going to be constants. So if you throw something with 100 meters per second, what changes how far it goes is the launch angle. So that's something that you may have talked about in physics. How do you know if you launch something at 30 degrees versus 60 degrees? How far is it going to go? So we talked about maximum height values a lot at the very beginning of our class, but we also want to know how far we can get things to go based off of how we launch them. So what I would recommend doing once you've identified constants in a setup is to just bring them out in front. Then you don't have to really worry about them as you take the derivative. So this is our original equation. Anytime we're working with optimization, we're going to go ahead and take r prime, so that's our derivative value. But we're taking the derivative with respect to theta, which means we're going to be taking the derivative of the sine component, and that v squared over g just comes along. So this is going to be v squared over g, and then when I take this derivative, it's going to be 2 cosine 2 theta. And I set that equal to 0. Then, just like any other optimization problem, I'm going to solve for theta from here. Now, the good news is v squared is constant, g is a constant, and 2 is a constant. So I can just divide all of those over to the other side, and anything divided by 0 is just going to go away, which is awesome. Because then all I have to think about here is the cosine of 2 theta being equal to 0. So from there, what I want to consider is really just asking the question, where is cosine equal to 0? And we know pretty well from our unit circle that that occurs when theta is pi over 2 or 3 pi over 2. So because we have this 2 out in front in the expression, if we have 2 theta equal to pi over 2. We're just going to divide by 2 on both sides. And our theta is going to be pi over 4. We can do the same thing with the 3 pi over 2. We can say 2 theta is equal to 3 pi over 2. And then when I divide this 2 over, that becomes theta is equal to 3 pi over 4. Now, really in this case, when you think about launching something, you're facing a given direction. So if you imagine yourself, kind of about to throw a football or something like that, you're facing this direction. And so your launch angle, you're really only measuring from 0 to 90 degrees. So if you're facing the right-hand side, it would be pi over 4. If you turned around and looked at this direction, it would be 3 pi over 4. So really the only solution that we have to care about is the pi over 4, because the pi over 4 is going to work whichever direction you're in. Oops. So that's our final answer that we're looking at. And so what that means is, if you are launching the projectile with a constant velocity, so I launch it with 50 meters per second, I'm going to be able to get it to go the furthest possible horizontal distance if I launch it at a launch angle of pi over 4. And so one of the things that you may have talked about in physics, if you did kinematics work there, is that the maximum, I guess we would call it launch angle. It's usually pretty well emphasized that that's going to be 45 degrees to get you that maximum range that you're looking for. So that's this problem. Really all we care about is the sine of 2 theta. That's all you're more or less maximizing in this case. So I hope that one is clear for throwing things in the air. The next one, part B, is asking you to think about pharmaceutical applications. So if you take a specific kind of pharmaceutical, how does the body respond, and how can that be represented using equations? And this is actually something that is very applicable in the medical field. And so if you go to college and take calculus, you may have to take what's called calculus for life science majors. And typically those classes emphasize applications like these. So what it tells us is that the reaction to a dose X of a drug is given by this equation, where A is greater than 0 and B is also greater than 0. So just like in the previous problem, you guys, what that means is A is a constant and B is a constant. So what I want you to recognize is that this would be no different than if this problem was set up like this. R of X is equal to, and then let's call A 2, so this was 2x squared, and then B was 3. So if we see that kind of setup, 2 is a constant, 3 is a constant, but for some reason, this is usually going to feel a whole lot easier to look at the first time. And the reason behind that is just that it doesn't have so many variables, and we know it's a polynomial, so we know it's easy to work with. The downside to that, though, and the reason that as you go further in math, you work with more stand-in constants instead of specific numerical constants, is that you want this equation to hold true for any scenario. So let's say that this is a reaction equation that works for multiple kinds of pharmaceutical drugs. So you might have one type of drug follow, have AB2 and BB3, whereas a different drug, A could be 20 and B could be 50. And so you could use the same equation and find general equations from that initial equation that work for any drug. So that's the reason behind using A and B instead of specific numerical quantities. But this, kind of subbing in of specific numerical values like 2 and 3 can be useful as you go along and you're trying to picture what is it actually representing. So here it says, what is the domain of the reaction function? So what I did is I just went to a graphing page like Desmos, and I did exactly that. I picked 2 as the A term, and I picked 3 as the B term. So what we see here is that we cross the x-axis at 3. And if I change this value, and I don't know if I can change while I'm typing, maybe if I go to this piece, I can change that. So let's say I change that 3 to be a 5. Notice that then that's when I cross the x-axis. So what I can tell is, okay, thinking about the equation, this is talking about the reaction. So the B value looks like it's controlling how long the reaction lasts for. So that would be what we're looking at there. So B is controlling the length of reaction when I change that. And then I can think about, okay, what does A as a constant represent? So again, this equation is supposed to represent your body's response to some kind of pharmaceutical. So if I change the 2 to a 3, it gets bigger. If I change it to like a 100, it gets really, really big. If I change it to 0.25, it gets pretty small. Or that's 0.22. So what that means is that A is really controlling how severe the reaction is or the amplitude of the reaction. So it's kind of like one is controlling how much your body reacts, and then the other one's controlling for how long it reacts. That would be one possible interpretation. Then it asks us to find for what value of R is a maximum. So here, if we're working with ax squared, let's go ahead and write this out. Ax squared times b minus x. I would just recommend distributing in. So you'll have b ax squared minus ax cubed. And then to figure out where a maximum happens, we're going to take the derivative with respect to x. So this will become 2bax minus 3ax squared. And we can set that equal to 0. So then let's bring over that 3ax squared. And then what I can do is divide by x here. So I'll end up with 2ba equals 3ax. I can divide by 3a, divide by 3a. And so what I end up with is x is equal to 2b over 3. So what that means is the maximum is controlled by the b value, so how long the reaction's happening, and doesn't actually depend on the constant value of a. So another good check there is, remember I initially when I was looking at the graph set the 2 as the a and the b as the 3. So that means if I just double check with those subbed in constants, 2b over 3 would be 2 times 3 over 3, or 6 over 3, which is 2. So I expect that my amplitude, my maximum value, occurs when I'm at that value. So real quick, if we go back and check that, this is 2 and this is 3. That was the first scenario I looked at. And that's what I have there. So my x value is 2. That's perfect. That's exactly what we were looking for. Then to find the maximum value, all we need to do is plug that 2b over 3 back into the r of x. So what you want to find for this is r of 2b over 3. And so then that's just algebra from there. For C, it tells us that the sensitivity of the body to a dose of size x is the derivative of this reaction expression. So what that just means is we already took the derivative. That was this guy right here. So the problem tells us that that quantity is what we call the sensitivity. So it says, when is the sensitivity a minimum? So that means we would really just take one more derivative. So sensitivity is defined as 2bax minus 3ax squared. We can take the next derivative to find when the sensitivity is the minimum. And that's going to be 2ba minus 6ax. And we set that equal to 0. So 2ba equals 6ax. Divide both sides by 6a. And so in this case, our a's will cancel. We can simplify that expression to b over 3 is equal to x. And again, you could sub back in if you want the actual output value. And so then we can think about when we're contextualizing derivatives in the real world, we're talking about reaction to a dose, so the body's reaction. And then you can think of the body's reaction over time being the sensitivity. So if your reaction is very, very quickly occurring over time, that's probably a more adverse reaction, so you'd be more sensitive to the given dose. So again, one application for physics, one application for medicine. And I think the tricky thing here, once more, is just worrying about how to handle constants that aren't written as 2 or 4 or 10, but are written as variable values. And then just knowing when you take derivatives, you treat those